This is 2003 Form B question 2, and there's a graph of two circles with equation x squared plus y squared equal 2, and one is x minus 1 squared plus y squared equal 1, and they give you the intersection so you don't have to do anything at all. So for part A, it's the area of R and involving one or more integral, and I believe this one is important. If you do it in like one integral, you probably lose point. And so first thing, probably divide the area into half, the shaded one and the not shaded one. So for the shaded one, it's a quarter of a smaller circle. So, or we can write the integral as, we know it's from 0 to 1. So let's put it in there. And if we arrange the smaller circle, which is this one, probably cut 1, this is cut 2. We isolate y, so we have 1 minus x minus 1 squared, but we have the square root of that, dx. And we have to find the unshaded area, which is right somewhere in there, and we know that the intersection is 1 1. So for a larger circle, it's from 1 to somewhere else, and we know the equation from the second equation, x squared plus y squared equal 2. So it's definitely x equals 0. I mean y equals 0. And when we plug x squared equal 2, so we can find x is equal to square root of 2. So we put it in here. And once again, we isolate y from this equation 2. We have 2 minus x squared square root of that. And you don't have to evaluate anything. We just have to put it down in there. And we're done in A. For part B, it's similar. We have one or more integral, but the only difference is respect to y, and that's a little tricky. But with respect to y, in terms of graph, we're evaluating the rectangles, the width of y, and we have delta x, and delta x. So how do we do that? You can see it's definitely from here, which is the bigger circle minus the smaller circle, and we have the y value. So we start from that. It's the larger circle minus the smaller circle. So same thing, we isolate the x this time from both of the equations, and we can minus the bigger one minus the smaller one, and it's integral from somewhere to somewhere. So if we isolate number 2 in there, it should be 2 minus y squared dy, and minus, I'm sorry, there's no dy in the equation because we are not done yet, and 1 minus square root of 1 minus y squared for the second one, the first equation. So we have this, and we put the dy. Now we figure out where's the range of this integral. We know that the maximum y value, which is this point, I'm trying to exaggerate a little, but this point is 1 1, and this intersections, it's 0, it's square root of 2 and 0, because we are evaluating dy, so we have to choose the y value, which is 0 to 1, and we put it in there, and we are done. For part C, this is much different. We are integrating polar equations, but those two polar equations are exactly the same as the graph. So I would draw a line just to divide the two parts. The shaded part, it's very easy. Remember the equation for a sector of a circle? It's 1/2 r square theta. In this case, r square, it's square root of 2. We square that, and we put a d theta in there, and we know that the larger circle start from 0 to 1, so the integral is 0 to 1. When I say 1, I mean pi over 4, because the angle in the shaded area is exactly 45 degrees. How do we know it? Because the intersection is 1, 1, which means the angle is 45 degrees, and if we change that to radian, which is pi over 4, and that's the shaded area. Now the unshaded area, it's the smaller circle. We know that because r equal 2 cosine theta, so we know that this point and this point are pi over 2 and pi over 4. So we know that this one, it starts from pi over 4 to pi over 2, and we use the 1/2 r square, and we can calculate the area, and it is as simple as that. If you don't have the time to look at the graph, you can look at it again, and that is easy.